Dr. Fossum, you have in the program, which I hope you picked up, a full introduction on him. What I wanted to say about him was this. When we were preparing for this event, I was looking for a speaker who could relate to our environment, who could talk about invention and innovation, who could share with us some first-hand experiences. I actually contacted, and I will apologize, Eric, I did contact someone else first, who wanted $20,000 to talk to us for 30 minutes, which of course was more than most of our patent budget put together. Therefore, I looked some more and I found Eric, and I was so impressed when I found his bio online and that he had recently received some significant recognition from the President. But I was most impressed by the fact that when I asked him if he would speak to us, he said, "Buy me a ticket and I'll be there. This is important." And that is the only introduction I'm going to give you, Eric, so please join me in welcoming Dr. Fossum.
Well, congratulations to all of you on your patents. It's a fantastic thing. Welcome to the club, I guess. And I am really honored to be invited to talk to you on this, your day of honor. And I hope that I can provide you with some entertainment in the process. I am here to tell you about my own story, journey, I guess. Exodus, I don't know what the right word is, but travel to commercialized technology that we invented at the NASA Jet Propulsion Laboratory, which is part of Caltech. This invention took place around 1993, which is the CMOS active pixel image sensor. And talk about, how long it takes for these things to get out. It seems like it's been a long time, but now you can get this technology in every cell phone, camera, most cameras, like the one that's down here, web cameras, you swallow pills to go through your body. So it's become quite ubiquitous, and but it took 20 years for that to happen. These things don't happen quickly, which, by the way, happens to be with the lifetime of a patent, in case you didn't know. Okay, yep, same thing. So as you heard before, necessity is the mother of invention. Usually we're trying to solve some sort of problem when we come up with an invention. In our case, the problem we had was spacecraft cameras. So around 1977, Voyager was launched, 2 Voyagers actually, and they are big spacecraft. You can see the spacecraft here, and the cameras that delivered some fantastic pictures. I remember over the years, in fact I have this picture hanging in my office anyway because it's such a nice picture, had very large cameras, much bigger than a bread box, and 38 kilograms, 35 watts of power. That's a lot of power when you're going out far from the sun. Big drain on the spacecraft, and makes necessary to have a big rocket also to launch these things. But then, fortunately, a few years prior to that, 1969, in fact, the CCD was invented, the charge-coupled device, which I'll now refer to as a first-generation solid-state image sensor. And the way these things work, I'll just take a moment to explain, is that we have a lot of electrodes on a semiconductor surface, and then there's a layer of insulator in between, not shown. And then we have charge, electrons, for example, in the semiconductor, that are drawn to the electrostatic potential on these gates. Sometimes I like to think of it as like magnets on a glass table that are holding magnetic filings up underneath the bottom of the table. And if you change the voltage on these electrodes, or the magnetic strength of the magnets on the glass table example, you can actually drag the charge as you pulse the voltages on these gates from left to right. And you can actually transfer the charge in the semiconductor over macroscopic distances. by pulsing these electrodes in a sequence. So that was interesting, and you can also use light to generate the charge that's in the semiconductor. So if you range a lot of these shift registers, you turn this around 90 degrees and let it shift down this way, and you put another one next to it, and another one next to it, et cetera, et cetera. And then you shine light on this like you would on a piece of film. You generate electrons proportion to the light intensity, how bright the light is across here. And then close the shutter quick, and then start shifting this charge down in all of these registers at the same time. And when they fall to the bottom, get to the bottom, we build another register just like this going sideways. So they all get loaded in, and then quick as a bunny, we shift them out to the corner of the chip and out an amplifier. And just repeat the process over and over until we've read out all of the signal across this entire image plane. So that was a pretty good idea. It was at AT&T Bell Labs, and in fact, it was recognized as being such a nice idea that Willard Boyle and George Smith both received the Nobel Prize in Physics in 2009. Here's some of their notes from their notebook. It used to be really important to keep a good notebook because in the old days, you used to get the inventor was the first to invent. That's not exactly true anymore. It's always good to have a good notebook, but now it's the first to file. So somebody else could have had the idea a long time ago. If they just sat on it, too bad. If you file it before they do, you win. But anyway, they got the Nobel Prize for the invention of an imaging semiconductor circuit, the CCD sensor. And I'll just digress for a moment, just only because, well, maybe there was a citation blunder. Nothing against the Nobel Committee. I'm sure tried hard, except that when Boyle and Smith invented the CCD, they were really thinking about a semiconductor analog of bubble memory and just shifting charge along. And they weren't really thinking about imaging. And in fact, it was Mike Tomset who worked with them contemporaneously that actually invented the CCD image sensor itself. And then this was the boss of both Smith and Tomset, who actually wrote something later about, well, I won't read it exactly. It's not really complimentary to the Nobel Prize Committee. But I always felt bad for Mike, and he came and gave a talk at our workshop just a few months ago. So, you know, it's good to be an inventor. It's good to invent. It's also good to get credit, and it's unfortunate when you get left out. But it happens to all of us from time to time. Anyway, back to our story. By 1989, which of course is 20 years after the CCD was invented, 20 years, there's that 20-year period again, Galileo was launched, and it had CCD cameras. And well, guess what? They're still big. And I forget where they went, somewhere around here, maybe over here. Large camera, actually this is mostly telescope at this point. There's another box of electronics not shown. Went out, took beautiful pictures, 800 by 800 pixels. Actually that seemed like a lot in those days, less than a megapixel. Still weighed a lot, 30 kilograms and 15 watts of power. So still a big load on the spacecraft. By 1997, the CCD got better. It was up to 1024 by 1024 pixels. But the mass grew. That includes the optics to 60 kilograms. And the power is up at 30 watts. And you know, the spacecraft also got larger and larger. In fact, I think this is kind of the spacecraft that broke JPL, in a way. It got so expensive and so time-consuming to build these that it was an entire career, practically, from the time you conceive of the experiment to the time the spacecraft is built and launched and travels out. In this case, Cassini went to Saturn, and you know, it's just taking pictures now. This is from a little less than a year ago. So these big programs were really weighing NASA down. They could only do a couple of programs at a time and consume the entire outer space exploration budget. So when Dan Golden came into NASA, I think it was about 1992 or 1993, perhaps 92, his mantra was faster, better, cheaper. And at JPL, that kind of came down for us to build instruments that were smaller and better, smaller yet better, and cost less. Part of that is just that if they're smaller, maybe they take less time to build, and that would, of course, reduce the cost. So we had to miniaturize these cameras on future spacecraft, and of course, that's good because smaller payload mass means smaller rockets, that's less cost. Smaller payload volume means less radiation shielding, so also less mass, so smaller rockets, also good. Less power means, especially for these far-out planets, smaller power generation on board, which means that whatever nuclear power devices they have on the spacecraft could be smaller and hopefully be more socially acceptable. Well, only in the event that they were to somehow crash. That was what people were worried about. It never happened, but people worried about it quite a bit. So, okay, now that's 1990s. The CCD technology had continued to evolve. This was a CCD camera from around that time, and the CCD, which is a silicon chip, is pretty small. There it is. Unfortunately, in order to make it work, you have to apply signals to it, lots of voltages and timing signals, and that consumes at least an entire board of electronics. And then when the signal comes out of the CCD, you have to amplify it and do a lot of other things to it, and that takes another board of electronics, and the whole thing is still pretty good size. I think anybody who works in electronics knows that integration, that is combining a lot of electronics onto a single chip, is a really good way to miniaturize electronics, and is what's been happening over the years. The only problem is that the CCD is not really amenable to electronics integration. What does that mean? Well, you could, and people did, try to integrate other electronics on a CCD chip. But the way you make a CCD with the doping profiles and a few other steps, it's really not compatible with mainstream microelectronics. And so you could run the chip through the fabrication process practically twice, once for the CCD part of the chip and once for the other electronics part of the chip, but that makes it very expensive and makes the, of course, there's a yield issue, and it's just wasn't commercially viable in any sort of way. So that was the mother of invention, was that necessity. And so that for a couple of different reasons, we came up with this new type of technology, which was, the long name is this, it's almost like Seuss, the CMOS active pixel sensor with intrapixel charge transfer camera on a chip, which is now just CMOS image sensors, where we can now have all the pixels on the chip, all the electronics required to drive those pixels, as well as to control the signal processing afterwards. It's on chip, including the A to D converter and programmable gate arrays and other things, which makes the entire camera shrink from something that's this size to something that is smaller than the fingernail on your littlest pinky. So I realize that probably not most of you are electronics engineers. Maybe you are, I'm not sure. But let me just take a moment to explain the basic idea of this. So we take a picture which gives us a brightness variation across the chip. And yes, these are my 3 daughters, in case you were wondering. We divide that area into lots of little picture elements, or pixels for short. And then every single pixel is basically consists of some silicon photodetector area. And the light comes in, and it generates an electron hole pair in the silicon. It's 1.12 eV band gap. And that current we use, one of those carriers we use as a current. And inside the pixel, then, we have the following electrical sort of circuit. We have a photodiode, that's this part, and it has some capacitance associated with it. And we have a voltage source, and we pulse the switch for a moment. I'm not going to take too long at explaining this, but just for a moment. That pre-charges this diode capacitance or diode to some voltage. We open the switch. We let the light fall on the chip, and that discharges this diode or discharges this capacitor through the diode. And so the voltage on that photodiode drops over time, proportional to the light intensity. And at the end of some time, like a 30th of a second or a 60th of a second, we read out the voltage. And the difference in voltage between where we started and where we ended is proportional to the light intensity. And that's the voltage we take to an A to D converter. So this second generation image sensor technology consists of an array of these photodetectors that convert photons to electrons, the amplifier, some analog signal processor to suppress noise and further amplify the signal. And by the way, I left one thing out in the explanation, was this intrapixel charge transfer, which is an important element of making these things low noise and scientific quality. Well, analog to digital converters, timing control, you saw all these things on the other chip. And getting them all together was very convenient. By the way, I didn't do this all myself. There was a team of people working here. Actually, in my case, I was actually already section manager, which is like assistant section manager. So there was like 100 people in our section. And for me, frankly, it was a bit boring to be promoted to that level. And so I started a little group on the side. That was one good thing about JPL, is you could do weird things like be a manager and still start your own little research group, which I started with 1 or 2 people, and all of a sudden it grew into a dozen people or so. And that actually worked out pretty nicely. So there we have this technology, and I should say that, boy, did we have a lot of problems. Not problems with the technology. The technology was easy. That was the easy part. We had like a problem inside JPL. There was a CCD group. And those CCD guys didn't like the fact that there was another technology challenging their turf. And they put up all kinds of internal barriers. And I'm sure all of you who work in a federal lab understand how that kind of thing can work. It's not like a lot of fun to deal with on a day-to-day basis. So we had those barriers internally at JPL. We had to like compete against the existing technology. Plus, there was the rest of the world in image sensors, all of which were CCD guys, because there wasn't any CMOS image sensor guys out there. And they all were threatened as well by this new technology. So just gaining acceptance out in the peer community was also difficult. I remember going to a conference in 1993, so it was just a little while after we had demonstrated this technology. And there was the chairman of the conference basically challenged me to an impromptu debate on stage about the merits of this new technology, telling me how he had worked in that area once before. It was a dumb thing to be doing. Why am I wasting my time doing this? Everybody knows it doesn't work. It was challenging, let me say that. Meanwhile, one of the other things we were supposed to do at JPL as a federally funded R&D center was to transfer technology developed in the federal lab out into industry, make ourselves relevant. Sound familiar? At least I had the religion about this particular technology. I thought for sure it was important and would be useful. So I started going out and talking to a lot of companies, trying to drum up interest. And actually, it was kind of a good thing, because in those days, the people making CCDs were all in Japan. It was kind of a Japanese industry by that point. Even though it was invented at Bell Labs, in the usual kind of American industry style, things kind of migrated out of the U.S. somewhere else, in that case, Japan. So all the camcorders and things that were coming out in Japan were driving technology innovations in CCDs, all in Japan. So we kind of like lost the recipe on how to make the CCD wine. The monks should not lose the recipe for the wine. It's not a good idea. But since this was a CMOS-based technology, we thought that U.S. industry could go back and maybe reclaim part of that image sensor technology market. So we talked to a lot of companies like National, Motorola, Intel. They were all quite interested in talking, at least. We actually did sign technology cooperation agreements with AT&T Bell Labs, Kodak, and a small startup, Schick Technologies. And that, all looked kind of interesting. Unfortunately, they also move slowly. At least maybe I'm just an impatient person. I don't know. But by 1995, I was a little frustrated that things weren't going as fast as I thought they should. And well, actually, I have to tell you the story behind the story here, which is that I was also part of my team was my wife at that time, and she was pregnant with our second child. She was actually out on maternity leave, and we started getting a lot of interest from people in this technology, wanted to know where they could get chips made. Even though the big industries were moving slowly, a lot of small things were coming up. So I said to Sabrina, why don't we just like get you a CAD terminal you can like work at home while you're watching the baby, and you know, maybe we can like make a little extra income while you're not working, so to speak. Okay, be careful about that. But oh, she's a very motivated person, so that appealed to her. So so we started this company, Photobit. It was a small business entity, her and me, in February 1995. So, and by the way, it's helpful to have one person who actually has a real regular job like I did at the JPL when you're starting a new company, because there's not much money at first. But we got this incredible lucky break, and I can't understate how important it is to have some luck in this process. If you talk to anybody who's had success, they'll tell you that really it came down to being lucky one day. Something happened that was just seemed like pure luck, and that really made the difference. And you can't control this. So it just either comes or it doesn't come. Our case, there was a reporter from Business Week who was visiting JPL, and he was looking at other things, and someone mentioned to him that, oh, maybe you should go down to Eric Fossum's lab. There's something interesting going on down there if you have some extra time. So he did at the end of the day. He came down to my lab, heard about what we were doing, spent about an hour there, and then wound up writing a 2-page article in Business Week on that technology, and which was very nice. And I asked him, I said, you know, by the way, Larry, this is by phone afterwards, you know, we have this little startup company at home. Could you possibly mention this company in your article? Yeah, sure, I'll do that, which he did. And that was a real lucky break for us. So that was all the super fun part. Then we kind of entered the perspiration phase, which lasted 6 years, which is hard work. Perspiration equals hard work. You know, you can't just give a technology to somebody and expect them to run with it. If you believe in it, it's really up to you to make it viable, and you have to work at it. So we started doing custom design contracts from private industry. We also, in time, were able to get support from SBR programs. If you've ever worked with SBR, you know it's not an instant process. You write a proposal, maybe a year later, you get a very limited amount of funding to do the work. Nothing to really rely on to build your business, but it's important support and gives you a degree of credibility as well. And later, as we got more and more successful, nothing succeeds like success, as they say. We started getting investment from strategic business partners to develop catalog products. And in the course of this 6 years, we also filed over 100 new patent applications. So maybe there was a 6 or 7, which are now considered fundamental patents at Caltech, but there was another 100 on top of that that we had to actually make the technology be fully commercializable. So again, a lot of perspiration. But the technology went into a lot of early web cameras. A couple of other fun places it went to is these are X-ray sensors, dental X-ray sensors. Remember I was talking about Schick as a little 3-person company. That company had grown about 600 people. By this point in time, if you go to the dentist and they put the X-ray sensor in your mouth instead of film, that comes from this technology. Another fun thing that we did was the pill camera. A company, just a few guys again in Israel, came to us and said, hey, we have this concept that they were actually former missile scientists. They said, well, we want to build a little a little pill or body missile, if you want to think about it, with a want to put a little seeker in the front, a little image sensor. Can you use your technology to give us enough imaging power, not low enough power to be able to do this? And it has to last for 4 or 5 hours on a battery that still fits on board this pill camera, and plus there has to be a radio to get the data out of your body. So you swallow this pill and it goes through your body, and every now and then, about once a second, it broadcasts another picture, which is received in something you wear on a belt. And it turns out the only way to non-invasively image your small intestine, so you don't actually have to cut you open to see if there's something wrong inside. It's turned out to be pretty good, and of course it's another good thing from a business point of view is that it's a disposable camera. So, well, there's another joke I'll tell you later perhaps about that camera as well. And then, and of course, the gigantic market that made all the difference in the world is the cell phone camera that needed a very, very low power camera that was very miniaturized to go into every cell phone. And that became the killer app for this technology, which really didn't emerge until, I would say around 2000, 2001, as it really emerged as the big application. As around the whole, again, it wasn't something I did by myself. This was the company around year 2000. This is in Pasadena, California. Finally, in November 2001, we were acquired by Micron. It also was not an easy process. It wasn't like somebody just came out of the blue and said, hey, we want to buy your company. How about that? You really have to actively market to your company and try to sell it. Turned out 2001 was a terrible time to sell from a semiconductor company valuation time. But several of the founders, not me by the way, wanted to sell, and so we did. I'm not really complaining, but we were having fun at the same time, so it was sad for that to come to an end. By 2001, there were many competitors because we spent so much time. I spent so much time on the road trying to explain to everybody how good this technology was that by 2001, people caught on, like, hey, this really is a good idea. And so the tech transfer process actually worked. It just took a really long time. An example, early adopters were Toshiba, STMicro, OmniVision. And then later, as is quite normal in high tech, is that the big guys came in at the end and then ate up the marketplace. Sony and Samsung, for example, now number 1 and number 2 in the worldwide market. Step 7, the technology has a life of its own. Today, about 2 billion cameras are manufactured every year that use this technology. That means more than 60 cameras per second all the time. Sales are about $7 billion in 2012, $10 billion in 2016. Here's the happy news for me. Caltech has successfully enforced its patents against all the major players. So, I have to stress this point also for my fellow inventors. People don't want to pay you royalties. They would rather just steal your technology and use it, see if you complain. And when you're a little fish and a big fish like Sony starts using your technology, you just can't sue them yourself very easily when you're a small company. Why? Because they have a pile of patents 10 miles high that all have to do is pick like 3 of them, and they can make your life miserable by countersuing you. So on the other hand, once we had sold our company and the IP is still owned by Caltech, they were able to go file lawsuits against these players, and eventually, over the years, they were able to generate some income. Actually, generate a lot of income. In fact, I think it's the highest income revenue source in royalties for Caltech. They feel like they should name a building after me. That's the way I feel. Because it's a lot of money. And here's another favorite bullet. NASA is now just adopting the technology for use in space. So anyway, here's just an example of these little cameras. Here's one that is another company I ran another company after I finished with Photobit called Simpel, using a MEMS-based autofocus technology. It wasn't my technology idea. I was just the hired gun to run the company. And then just 5 years later, here's a 16 megapixel camera module. Here's a 1 centimeter scale. Amazing, from Sony in 2012. Here's an endoscopy camera in 2012. And for all you guys, I'm sure you understand why it's important to have cameras that are that small. I don't want to finish this talk without just, well, I'm going to mention two things. But the first one is just that new technology brings about new social issues. It's kind of a something that you just don't expect things to happen. And yet somehow you're kind of, I guess, I'm responsible for some of these things, in good and bad. And you know, as scientists or engineers, we can't usually foresee the consequences of the technology that we create. And like I said, some of it's good and some of it's not so good. And you know, you wonder about people in the past, especially in the higher energy physics area, you know, about technologies that are created that people don't really foresee what the good and bad can be. I don't have a conclusion really about that. It's an interesting dilemma that we have as inventors. But you know, certainly communications have changed. Rapid social change with visual feedback that's just so instantaneous in the political arena. Inappropriate use. I mean, who would have thought? I mean, it's amazing to me. Visual overload, where you see more than maybe human beings really can digest. I mean, we're just not used to seeing all this terrible stuff, perhaps, so frequently. Security versus privacy, a big, you know, continuing debate, I'm sure, about those two things. And, of course, the possibility of new kind of unpleasant weapons, perhaps, to think about. You know, this is like, maybe this is a little spider that crawls around and injects poison in people to, you know, eliminate bad people, or maybe just spy on people. I don't know. But people are definitely working on this. That's one note. The other note is that I am pleasantly and always surprised that there seems to be some use of this technology in high energy physics. I have to say that some of the ideas that I had about CMOS image sensors came from the high energy physics community at first, certainly in the area of hybrid arrays. And then I think the work we did on monolithic CMOS active pixel sensors has fed back into that community. So it's been a nice synergistic relationship over the years, since the 80s, I would say. Cheesy metrics. I mean, I don't work on colliders, so there's 104 hits somehow and there and somewhere there. Probably half of those came from Greg Depthick, who's here working there. You have your own local expert in that area. And if you want to learn more, there's some gigantic recent review article on this. Oh, I was going to mention, what am I working on now, by the way. I'm continuing to work in this field. This is maybe a third generation image sensor, I don't know, but we're trying to detect every single photon that hits the image sensor. So we build very, very tiny pixels, maybe 100 or 200 nanometers across, to detect just a single photoelectron. So it's just binary, a 0 or a 1. And then we also read it out at thousands of times per second. So this image sensor might have 1 gigapixels or jots read out at 1,000 times per second. And don't ask me why I can't do the math, but about a terabit per second of data. And now pixels are defined in time and in space by software. We don't have a physical silicon collection area anymore. It's far below the diffraction limit. We can just kind of arbitrarily set how big our window is and have basically zero read noise in reading out things. Lots of interesting challenges there. So in summary then, this was a mock-up of a camera that was in that Business Week article. that the machine shop made out of aluminum in 1995. 15 years later, we have the real thing, including autofocus, and from the Voyager spacecraft to perhaps fantastic voyage. So thank you very much.
We have time for a couple of questions, and after we do a couple of questions here, you are all invited to the second floor. We have a cake up there for our award winners, and Eric's going to be joining us up there, so you'll have a chance to talk to them in a more informal environment. But we do have time for a couple of questions.
Thanks for a great talk, Eric. How many times did you fail?
Never. What are you talking about? At JPL, when we were building these image sensors, we tried a lot of different things, different combinations. It wasn't clear what the right choices were for some things. So I wouldn't call them failures, but let's just say that we kind of helped figure out our own roadmap in the process. In the company side, I won't say we failed there too often either. Most of the chips that we built, custom chips, were successful, but sometimes we were late, so that was kind of a failure from the customer side. We failed on the business side a number of times. We spent resources on developing something that didn't actually go anywhere. I mean, in the early days, we didn't even know there were no conventional sizes for image sensors. It was kind of like, well, 640 by 480, everybody knew that. That was VGA. And there weren't like clear sizes after that. So it was like, oh, make the next product. Well, what size should it be? And we guessed wrong sometimes as to what the industry standard would turn out to be. A lot of things we could have done better. So I wouldn't call them failures, but I learned a lot. Actually, that's why I went back and did that second company, so I could like show that I learned something through that whole process.
How did you navigate conflict of interest between Caltech and Photobit? And second, how did you deal with, there's a lot of predatory venture capitalists, and how would you go about that now?
Okay, so the conflict of interest thing is very important. In fact, there was just a really interesting article in the New York Times yesterday about a guy down in Georgia Tech who was like arrested. He was a professor. And he's not even sure why yet, 2 years later. It's kind of an ugly story, but it's in the New York Times yesterday. Well worth reading. In our case, fortunately, I was a Boy Scout, and I really went out of my way to make sure people knew what I was doing and what we were working on. It was not easy because Caltech, through JPL, had never licensed technology at JPL to the inventors. They thought it might be a conflict to give a license to the people that invented it. Fortunately, they decided that actually it wasn't such a bad conflict, that the people that were most likely to be successful at commercializing a technology were the inventors, because that was the easiest path for tech transfer. And we were actually the guinea pig for that operation. They created their Office of Technology Transfer almost simultaneously with us being the test case. But it was very important to have a lot of open communication so everybody knew what was going on. And I was very careful that the first year, actually, we started the company, but I stayed at JPL for a year. And that was a really tricky year. I mean, there was a lot of things that had to be separated from my responsibilities, so there wasn't any perception of a conflict of interest, which is what counts in a federal lab. Not whether you really have a conflict, but if someone even just thinks you have a conflict. In my mind, what always kept me straight was the sound of that tick, 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 60 minutes interview with Mike Wallace that I did not want to have. So anyway, I think it's easy to get in trouble. Conflicts, there's a lot of temptations, there's a lot of slippery slopes. And you really have to be vigilant about keeping everything above board and just going overboard in terms of avoiding even perception of a conflict of interest. And your second question, I've already forgotten. Oh yes, the VCs. So now I'm at Dartmouth at the Thayer School of Engineering, and right next to us is the Tuck School of Business. All the Dartmouth Board of Overseers are all successful venture capitalists. All the big guys at the Tuck School of Business are all successful financiers of various things. I found that there seem to be really good VCs out there that really care about building business and value and that sort of thing. And then there are VCs, not any that I've encountered at Dartmouth, knock on wood, but I have encountered in the second company that I ran, because that was a venture-backed company, that are less scrupulous. And it's difficult. And as a CEO, which is like my job at both companies, but since we didn't have VCs at Photobit, I just talk about Simpel, is you have to really take what they say with, in a way they're your boss, right? They're on the board of directors. Theoretically, the CEO reports to the board of directors. But a CEO really has a responsibility not only to its board, its shareholders, but it has a responsibility to its employees and the people that work there, because you've created a family, your own little tribe. I remember when in Simpel, the second company, after we built the company up from like 12 or so up to about 40 or 50, we actually had a family event. We had like a bowling thing where employees brought their families and everything. And my wife and I walked in, and it was already well underway, and there was kids running around and families and everything. And she turned to me and said, "You better not screw this up." You have a responsibility to these people too. And as CEO, you have to balance these two things. And predatory VCs are predatory. And in the end, the reason I left Simpel was because I developed a conflict with one of our board members. He told me to lie to an investor, and I said no. And that was the end of that. So you have to choose your own moral compass.
I have a question about the difference between publishing and filing patents, because we are employee of federal laboratory and we are encouraged to do both. How would you divide your tasks?
Right. Well, first of all, you realize that a patent is a publication. By the intention of the patent system, the only reason why you're granted any exclusivity is because you've agreed to publish your technology to everybody else. So you get a limited period of exclusivity in exchange for publishing that technology. That's what a patent is all about. So a patent really is a publication. Second, someone needs to check the rules lately, but I believe that there is nothing about a publication that invalidates a patent as long as you file promptly. I believe it used to be that you had a year after a publication to file. I think it's probably still true. The only thing you have to be careful about is someone else doesn't file before you. So you can file a provisional application, which is pretty much the paper that you're going to publish, for like $300 or something like that. It can get filed, you protect all your rights, and then you have a year to decide to proceed with a full application. So it really should not be a conflict between publishing and patenting. As you know, I published a lot of papers at JPL, and we still, collected some nice royalties. So it's possible to do both. It's always good to, I'm not sure what the system is here. Jerry and I were talking about it earlier, but there should be a very low impedance path, speaking as an electrical engineer, low impedance path that goes through a technology office just to capture any important technology before it goes on to get published. It might result in a week delay. It might mean you have to plan your conference abstract to be finished more than 10 minutes before the deadline of the conference. But not a lot more, you know, probably just a few days or a week if Cherry's office is funded and up and running.
Working on it.
Yeah. So I don't see that there's any conflict at all between publishing and patents. Now, trade secrets, which is a different kind of IP, is not a patent. It's important, like Coca-Cola, right? The recipe for making Coca-Cola. It's not patented. It's just that nobody knows. It's a trade secret. That's a different kind of intellectual property. But patents and publications, no conflict whatsoever.
Okay, I think that. Eric, I want to thank you so much for joining us today.
My pleasure.
And again, I want to encourage everybody. We're up on the second floor. We've got a really lovely cake for our champions of innovation. Also, for those of you who were recognized for your records of invention, believe me, we did not forget you. There are certificates and checks for you as well. Come see me on the second floor to get yours. Thank you.